Hello everyone, my name is Elena Pagnin and today I will be presenting our recent results on secure generalized deduplication via multi-key revealing encryption. This is a joint work with Daniel Lucani, Lars Nielsen, Claudio Orlandi, Rasmus Vestergaard and myself. Let me introduce our setting. We have an Alice and Bob. In our case, Bob is a user with a smartphone or a device where he has stored his important files, data, emails, pictures. And what often happens when you store everything on one single device is that you soon run out of storage space. And of course, Bob is not happy about that. What Bob would like then is to minimize his local storage. Lucky enough, Alice can provide such a solution in the shoes of a cloud service provider. Bob can outsource his data to the cloud, store it there, remove it from his local device, and then gain more space as he wanted to. However, on top of this standard setting, we could also have that Alice may wish to minimize the global storage on her side. So imagine that there are many users using the same cloud service provider, then maybe Alice wants to minimize the total storage space required to store all the data. So Bob may want to retain his privacy on the outsourced data. This is the setting we work with. So luckily for us, there are already solutions on how to minimize the global storage, in particular compressed data, so represent the same data in less space. Let's consider for instance, this pile of files is made of 4 different files that have quite some overlapping, but still some lines different. This is, for instance, the case when we use Git or SVN and we update a file. Usually we change a couple of lines, but most of the file is the same. In this case, the standard storage solution without compression implies that each file is stored as a separate file. So taking, let's say, 4 times the space needed to store one file. A different approach is to use generalized deduplication. In this case, we are storing the first file as the mother somehow footprint. And then we store just the deviation of the other files. And of course, we want to have some pointers to know which was the original file and where the deviation happens. Experimental results show that on correlated data, this generalized deduplication technique achieves a compression of 15 to 20%. So we basically need about 20% less storage space to store exactly the same information. However, this star is very important. This only works on correlated data. For instance, an image dataset, a Git repository, and so on and so forth. Because if we had completely uncorrelated data, then of course we cannot compress it. But what about privacy, you may ask? So let's recall our Bob with his files. He might have some files that are private, and the standard thing to do when you want to preserve the privacy of something, well, before outsourcing it, I can just simply take my file and encrypt it. That's the very naive way. So let's see what happens in this setting. Now, when Bob outsources his data to the cloud, there's going to be the same plaintext data as before, where Alice can run on generalized deduplication and compress the total storage space. However, there are a couple of files that are completely gibberish, because if we use a secure encryption scheme, what happens is that the ciphertext looks completely unrelated to the plaintext. And this doesn't make Alice happy, because when the data looks random, or the power of generalized deduplication decreases, so we don't have the same compression ratio. And the setting we consider in our work is actually a multi-client setting. So what if every user of the cloud service is encrypting the data? For instance, they have sensitive cooking recipe they don't want other people to read, or they're analyzing data in their labs and they don't want other people to read it. Then the situation gets even worse, because Alice cannot deduplicate even across different users. And then the space required to store all of the data becomes gigantic. The solution we propose is a new cryptographic primitive to address this problem and similar problems, which is multi-key revealing encryption. A summary of our contribution in this work. Our first contribution is a definitional model for multi-key revealing encryption. This is a new primitive that somehow extends and builds on top of revealing encryption, but of course needs to be formally defined. As a second contribution, we provide a generic construction of multi-key revealing encryption from message lock encryption, deterministic encryption, and randomized encryption. So in a nutshell, we provide a compiler that takes a message lock encryption scheme, a deterministic encryption scheme, and a randomized encryption scheme, blends them together in such a way to obtain a multi-key revealing encryption scheme for the generalized deduplication functionality. Then we show how to instantiate our compiler using hash function solely in the random oracle model, and we prove our construction secure in our security model. Finally, we provide an implementation of our construction for generalized deduplication and do a performance analysis on a database that is publicly available of images and test how the solution behaves with respect to no compression and generalized deduplication without any privacy. Okay, so let's look at multi-key revealing encryption as a primitive. You can think of multi-key revealing encryption as a standard encryption scheme equipped with an additional comparison algorithm. This means that we do have a possible setup, a key generation, an encrypt, and a decrypt, plus this comparison algorithm. And this comparison algorithm depends on a revealing function. This means that in order to define a revealing encryption scheme or a multi-key revealing encryption scheme, we need first of all to give a revealing function. And this is a function that in this case takes n plaintext messages and returns a value in V. We have an algorithm called reveal that takes as input n ciphertexts and returns a value. Now, for revealing correctness, it better be the case that this value returned by the reveal function is actually the function compute on the messages. So just to give a concrete example, imagine that the function f is can I deduplicate these messages, these chunks, these files, well, somehow encrypt these files, and then I have a reveal function that tells me, okay, yes, you can deduplicate this ciphertext, or no, this ciphertext you cannot deduplicate. This property of having a comparison algorithm is actually shared with other primitives. For instance, searchable encryption, predicate encryption, functional encryption. But in this small table, I will only focus on primitives that have some multi-key functionality. So I will be comparing multi-key revealing encryption versus decentralized multi-client functional encryption and ad hoc multi-input functional encryption. So the first thing that we notice is the function f, the revealing function, what we called before. This is fixed in the multi-key revealing encryption, which means given an f, I can construct a multi-key revealing encryption scheme precisely for the f, tailored for the specific functionality. While in the case of multi-client and multi-input functional encryption can be instantiated for any function, for generic functions. However, those instantiations rely on fairly heavy cryptographic tools like indistinguishability obfuscation and multilinear maps. Therefore, in recent years, researchers have started to focus on schemes that work for a specific functionality. And here I just cite 2 papers out of the many that are out there. Chotard et al. Made the first decentralized multi-client functional encryption scheme for the inner product functionality only. And Agro et al. Have the first ad hoc multi-input functional encryption for also specific functionality. The evaluation function, this reveal function that I called before, in the case of multi-key revealing encryption, this evaluation is public, so everybody can run the reveal. Everybody can check whether n ciphertexts have or not the property that the revealing function carries with. While in the case of multi-client, multi-input functional encryption, this evaluation is private. This is usually linked to using the secret key connecting to the function f. Regarding how we encrypt files, well, in the multi-key revealing encryption scheme, this encryption is dependent on a secret key, while in the schemes that derive from functional encryption, the original ones were using a public key encryption scheme, and then for efficiency, they're moving towards secret key encryption solutions as well. Regarding the multi-user functionality, multi-key revealing encryption basically works for any number of users, so we don't actually count users into the ciphertext. While multi-client functional encryption is very clear where users' contribution needs to be. So there is like 1 user per slot, and functionality can only be computed if all users produce ciphertext for the same tag. So it's a little involved, the semantic in there. Regarding multi-input functional encryption, yes, this works, of course, for multiple clients, but again, the multi-input means I have a functionality which takes input from n clients, and client I can only give his input on the ith input of this function, so there is still 1 user per slot. Finally, multi-key revealing encryption does not need a master secret key. Of course, we can instantiate it with a master secret key to have further efficiency or an easier way to distribute keys. However, our construction and the general model does not require a master secret key, while multi-client and multi-input functional encryption do require a master secret key. There are variations where we can substitute this via multi-party computation protocol, so to generate this key, or basically split the master secret key into a lot of master secret keys, so there is no one central point of failure. However, the cryptographic primitive inherently requires a master secret. Let's look now at how we define security for this new cryptographic primitive. We consider an ideal versus real-world security definition with a simulator and so on. So the adversary is given access to a corruption oracle, a random oracle, and an encryption oracle. So in the ideal world, the simulator also has access to a L function. This is the leakage function, which is a functionality connecting to revealing encryption schemes and therefore also to multi-key revealing encryption schemes. This leaking function takes as input arbitrary number of messages, actually in our instantiation exactly the queried messages, and returns the value of the function f on this set of messages, of any set of n such messages. In a nutshell, the leakage function is returning exactly what the simulator, the adversary, whoever would learn by running the public reveal algorithm on the ciphertext. There are also a couple of security pillars that are unique to multi-key revealing encryption or particular there. So first of all, the simulator has only access to the leakage function LM and not directly to the messages, which means that when the adversary wants to encrypt a message, it will talk to the encryption oracle, but what the simulator sees is not the plain text message queried by the adversary, but rather the leakage of this. This is crucial in order to ensure that real-world ciphertexts only reveal the desired information about the plain text, and nothing more than that. Second, both the adversary and the encryption oracle have access to the random oracle. This change is a drastic change from the current revealing encryption models, and we did it because we wanted to enable a formal handling of a scheme that adopt deterministic cryptographic primitives. This is, for instance, what we will use for generalized deduplication, and we want that our general model can handle such schemes. Our adversary can perform encryption queries only by interacting with the oracle, so the random oracle, the encryption scheme, or when I'm in a reduction with the challengers that will then talk to the random oracle or the encryption scheme accordingly. This trick enables us to know everything that the adversary knows, basically, because we know what the adversary is querying the oracles, although we don't learn the plain text messages, but we learn the leakage of it. And as a downside, however, this means that we need to deal with idealized primitives, so we really need to work in the random oracle model. Another weakness is that we cannot mitigate frequency attacks. If we have an instantiation of multi-key revealing encryption that deals with the deterministic primitives, we cannot prevent the adversary from running a frequency analysis and check what is the most common ciphertext, and of course this will correspond to the most common plaintext or the message that has higher probability according to the message distribution. I told you that there is generalized deduplication as a technique to store, let's say, files in less space, but I never told you how it works. So let's have a little look into that. So generalized deduplication is defined by a transformation, phi, that essentially does what this picture is showing. So given two messages, it tries to point them to the center of the ball, let's say, they belong to, and then stores the deviation. So a bit more formally, this function, the transformation phi, will take as input a chunk, which is a file, a message, and returns a base and a deviation. And for compression interests, we would like that the deviation is fairly small, so this value L is smaller than K, which is the size of the bases, and that the way we split our message into base and deviation doesn't have much of a overhead than with storing the actual initial message. So what is the revealing function for generalized deduplication? Recall the revealing function is something that works on ciphertext and returns a value. And what would this value be? yes, I can deduplicate, or no, I cannot deduplicate. And the way I know if they are deduplicating or not is by checking if they have the same bases. So if I split the transformation phi into phi1 that return the base connecting to a certain message or chunk, and phi2 that returns the deviation with respect to that basis of my message or chunk, I'm just checking that phi1, that the two messages, the two chunks I given inputs, have actually the same image under phi1. Now our construction for multi-key revealing encryption for generalized deduplication. In our construction we will use 3 ingredients, as we said before: message locked encryption, which is represented with this rhombus, deterministic encryption, which is represented as a pentagon, and a randomized encryption, which is represented as a circle. And this is the way we do our construction. So we have our chunk, we apply the generalized deduplication transformation phi that returns a basis and a deviation. On this base deviation, we apply our encryption scheme, which works as follows. I use the message lock key derivation scheme, number 1, to derive a message lock key from the basis B. So chunks that are similar will end up in the same base, and the same base will produce the same message lock key, message derived key. I will use the message derived key to encrypt my bases and get a ciphertext beta. Then point 3, I will deterministically encrypt my message derived key. And finally, I will take the deviation and encrypt it using a randomized encryption scheme. So let's look for revealing correctness. What we want is that if I take 2 ciphertext, I can get to this 0, 1 function that we saw before. 0, I cannot deduplicate. 1, I can deduplicate. Well, what do I need to do that? If I can deduplicate 2 chunks, this means that they have the same basis. However, if they have the same basis B, they will produce the same message-derived key and the same ciphertext beta. So I'm just comparing the ciphertext beta. If 2 chunks have the same basis, they will have the same ciphertext beta. If not, they will have different betas. So very easy. I also show you very quickly how to instantiate this construction using solely hash functions. So first hash function that we use is we hash the basis to get a message lock key, message derived key. Then the deterministic encryption on the top. I will basically do a one-time pad with this message lock key and another hash function that uses the secret key and the ciphertext beta, which the ciphertext beta I produced using hash function number 2 on the message lock key, one-time pad with the basis B. And finally, for the randomized encryption, basically what we are doing is like sampling a random IV initialization vector and then doing another hash function with the secret key, initialization vector, one-time pad with the original deviation. Easy peasy. And we can prove that this construction is secure in the random oracle model. Now let's jump into the experimental results. We check 2 properties of our scheme. The first one is the compression ratio, which is measuring the compressed size after I apply generalized deduplication or secure generalized deduplication by using multi-key revealing encryption over the original size of the database. And as this picture shows, we expect to have a little bit of a drop. So the blue line is generalized deduplication and orange line is generalized duplication with multi-key revealing encryption of chunks of size 1 kilobyte. And we see that the generalized duplication with multi-key revealing encryption, so secure generalized duplication, is a little bit higher up. This means that if I have a database that occupies 100%, I need 89% of the space to represent it. While if I was just using generalized duplication without any privacy on top of it, I will only need 86% of the storage space. Our experimental results show that the gap between plain generalized duplication and secure generalized duplication is always below 3%, and usually way lower, as you can see. For chunks of 8 kilobytes, plain generalized duplication and secure generalized duplication basically behave the same with respect to compression ratio. We also analyzed the throughput, so how many seconds does it take to retrieve 1 megabyte if we have no encryption and if we have multi-key revealing encryption on top. So again, plain generalized duplication and secure generalized duplication. Of course, we have gaps, but the interesting thing is like these gaps is about 6.9%. This means that if in 1 second we can reconstruct a 15 megabyte file from a dataset which is encoded with generalized duplication, adding multi-key revealing encryption on top of that in order to have security, we will be able in 1 second to retrieve a file of 13 megabytes. So the difference is fairly small. And of course, our implementation was not optimized for throughput, so we assume we can actually get way better than what this figure shows. That was all. Thank you for listening, and I welcome any questions. You can contact any of the authors. Have a nice day.